So in this part of the lesson, we're going to actually move on to looking at how we'd calculate enthalpy changes in solution. And again, this is all centered around Hess's law. In other words, you can have various or multiple pathways that something can happen, a process or a reaction can happen. And even if you're not able to calculate one pathway, you can find that value by looking at an independent or a different pathway. Now, we will need to go over two enthalpy concepts before we can do these calculations. One is obviously the enthalpy change of solution, which you've probably got an idea now what it's about. It's about the energy required to actually form a solution. The other one is a concept called enthalpy of hydration. So this is a definition that you're obviously going to need to copy down. It's slightly different from the way they've worded it in your textbook, but the concepts are identical. So the enthalpy change of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to give a solution of infinite dilution. Okay, remember, as always with these definitions, you need to have the specifics outlined. You need to say things like 1 mole. You can't get away with not saying that. So to take an example, we've already been looking at sodium chloride. So let's look at sodium chloride again. There's sodium chloride in its standard state. What you're saying is you want to do this. You've got to break it up into its ions in their aqueous solution. Aqueous obviously just means mixed in with water, dissolved in water. Now that's how I'd write it, but I've just looked at your textbook and it's also asking you to write plus AQ, which is representing the addition of water. I haven't seen that before in other course books, but I guess if it says it in the textbook, we better do the same thing. Okay, so we've got plus AQ there. Now remember, these enthalpies obviously have a value. It's an energy you're talking about here. And the value for sodium chloride is plus 39 kilojoules per mole. And that's significant because we need to realize that these values are going to tell us what's going on. The fact that this is a very low positive value tells us that sodium chloride is soluble in water. What you should be looking for your delta H solution, and also you're going to have to remember that this is the way we write it, delta H sol, you're going to be looking for values that are either negative. These should be either negative or slightly positive, it's taking me ages to write there. So if you've got a value that's negative or slightly positive, that means that you're going to be able to describe that compound as being soluble in water. So you're looking for values that are negative or slightly positive. This one here being slightly positive, so a low endothermic value. This shows that sodium chloride is going to be soluble. Now, you have to remember that if a value exists for delta H of solution, then obviously there is a degree of solubility. So we kind of use the word soluble, insoluble in a very black and white way, but anything that does have a value for delta H of solution does have some degree of solubility. But obviously we don't say that. There's many compounds that are so bad at dissolving in water that we just describe them as being insoluble. Okay, so now that you've seen me do a very quick example of how we'd kind of illustrate by writing this form of equation, can you please write the enthalpy of solution or express enthalpy of solution of sodium fluoride as an equation like I have done here? And also, can you find out what the value for enthalpy of solution of sodium fluoride is? And tell me if you think it's going to be soluble or insoluble. Okay, so hopefully you've just written down this, nice and simple, NaF. You have to remember to put plus AQ as it's expressed in the textbooks. It's going to make Na plus AQ. Obviously, state symbols here are fundamental. If you don't put state symbols in, you're getting this wrong. Plus F minus, again, AQ. If you did a quick Google search, you would have found out that this value is around about minus 10. And if we follow kind of that general rule of if it is negative or slightly positive, then it is soluble. So sodium fluoride is indeed soluble in water. And that's what you would expect anyway from your original knowledge of the fact that ionic substances are almost always soluble in water. Okay, now we'll move on to look at this second key bit of information, the enthalpy of hydration. I'm just going to read this out. The hydration enthalpy is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. Hydration enthalpies are always negative. I've added that in there just because I think it's so important to remember. So if we were looking at, let's say, sodium fluoride again here, NaF, we're looking at any relevant enthalpies of hydration for this. So let's look at the definition. Enthalpy change when 1 mole of gaseous ions. So we're talking about having 1 mole of gaseous ions, like so, dissolve in sufficient water to give an infinitely dilute solution. In other words, we're going from that to this. Okay, again, state symbols are fundamental. You don't have them, it doesn't make any sense. So that would be the one for sodium ion, and then we obviously need our enthalpy of hydration for our fluoride ion, again from its gaseous form to its aqueous form, like so. And I've just added in there plus AQ and plus AQ because that's representing the addition of the water there. Now we need to think of what's going on here in terms of steps in an energy cycle. Here we've got an ionic compound, doesn't really matter what it is. You can say sodium chloride again. Now in order for me to go from this ionic compound here into having it into a solution, we can think of it in steps. So first of all, we can think about separating, whoops, I don't want those, I'll just get rid of those ions there. We've got to think about separating these first, okay? In other words, going from that solid state, if I put them back together now, right now they're effectively a solid, aren't they? Now obviously this would be a lattice, but I'm just showing a pair of ions there stuck together. We're going from that to this, where we break them up. I'll copy. We want to break these guys up like so, okay? Now, if you've broken them up like that, then we're assuming a huge distance between these. So they are now broken up into their gaseous ions. And then the next thing we've got to do is to surround these with water molecules. So if I just copy and paste those in there, the next thing that's going on is that the water molecules are forming bonds between them and the ions. I will put the charge in here just to make it very clear what we're talking about. So that's our positively charged ion, that's our negatively charged ion. Remember the dipoles here, is this is the negative part, that's the oxygen. This is the positive part here, those are the hydrogens. So in this case, down here, we'll have this orientated like so, like that, and we'll have a number of those, won't we? We'll have loads of these surrounding the positive ion, something like that. I'm not going to carry on finish it, it's taking a lot of time. And then we'll have it the other orientation here, where we've got the positive part of the water molecule latching on to this negative ion. So I have to orientate this slightly differently. Something like this, something like this. So that's what we're going for. We're going from, this is the solid state, we're breaking it up into its ions like so, and then and obviously that involves an enthalpy, an energy change in order to do that. And then this involves an energy change going from those broken up scattered gaseous ions to latching on the water molecules to them. And that also involves an enthalpy. And really the whole, if you look at the net change in enthalpy, that really gives us our enthalpy of solution. It's the net enthalpy from going from this right here, whoops, this right here to this right here. Okay, I should really put in AQ here just to make sure we understand. Right, I'm going to stop this video there because I'm worried it's going to crash again, and then we'll look at actually how to do these calculations in a second.